Swayam Prabha. Digital India. Educated India.
Good morning. We will continue our discussion of non-intrusive techniques, measurement techniques applied to sprays. We will first start by making a quick list of some of the techniques that are commonly used, and then we will look at the theory and principle of operation of those instruments. We have already looked at a couple of different non-intrusive measurements. We looked at videography or photography in more specific sense. We looked at particle tracking velocimetry. As well as particle imaging velocimetry. The particle imaging velocimetry is a technique that is used to obtain the velocity field given a certain set of particles that are in motion. But for the specific case of a spray, we are also interested in size. So, there are techniques, there are algorithms that have been developed to sort of ride upon particle imaging velocimetry algorithms to give us both size and velocity information. So, one very simple particle sizing algorithm in a PIV system is to use the scattered light intensity. So, think of a spray. And I am looking at a certain region in this spray, which is my image, and in this image I may have some large drops and some really small drops. Now, mind you, we are looking at a PIV, so we are not at a level where we are able to see individual drops. So, it is sort of a picture that gives us a grayscale intensity. And in this grayscale intensity picture, if I take a certain region of the spray, I have a certain grayscale distribution of light, and this grayscale distribution of light gives me the intensity in an image like this is proportional to d squared, where d is the diameter, and this comes from what is called me scatter. So, if I take a just to understand me scatter, if I take a spherical drop and subject it to a bunch of light rays, I have the possibility of a reflection at this surface followed by a reflection again, I have the possibility of a refraction at that surface followed by refraction again at the second interface, or I have the possibility of just reflection at this surface, or I have the possibility of refraction at this surface, a reflection at the second surface following the first refraction, and then I could have another refraction at this surface, or depending on the situation here I could have like total internal reflection followed by refraction. There is a whole combination of physical phenomena that come into play when I have a set of light rays encountering a spherical transparent object which is capable of both reflecting and refracting at the interface. The combination of all of these effects as well as gives rise to what is called a me-scatter pattern. That is, if I plot the intensity of the light as a function of the 360 degree angle going around the drop, it is known that there is a lobe at the center along the axis of the light. I will move this to the next page so I can. There is an intensity lobe at the center line. Let me use another color. There is a second lobe which is smaller in magnitude, but slightly off axis. There is also a third lobe which is more predominant at the backscatter level. So, if I plot the intensity versus theta, theta being in some sense this angle, I have the maximum intensity on the center line. And as I walk around this center line away along a clock away from theta, the intensity initially decreases, reaches what looks like a minimum and then increases. So, this is called the first lobe and this is the second lobe of me-scatter. There is also another lobe that follows from the backscatter mode. So, where light is for light to reach this point approaching from my left hand side, the light essentially we are looking at what looks like backscatter, scattered light coming back towards the source, whereas the first and the second lobe are more forward scatter lobes. Now, this pattern would be symmetric, as symmetric as my figure looks, and this symmetric distribution about the axis has these distinct lobes which can be observed. So, if I have a spherical particle suspended, let us say in a shaft of light, as I walk around I will see the specks of light appear brighter and then dimmer again when I approach one of these minima and then becomes brighter again. This is classical me-scatter pattern. So, if I now look at this image, so in this case let us say I have this light sheet approaching from the top, this light sheet approaching from the top, and if my camera is placed vertically where your eye is at this moment, then the image formed essentially is as though I am looking at this from a 90 degree scatter point of view. So, if this is my camera, I am looking at a spherical entity sitting here, receiving light from the top and scattering light towards your eye, and that is in this schematic it looks like a near 90 degree axis. And so, the intensity of the light scatter at the 90-degree position without, if I do not change the angle, the intensity of the light scatter at that position varies with d squared, varies as the diameter of the drop squared. So, it is essentially a phenomena where the intensity is proportional to the surface area of the drop. And if I receive if I receive different amounts of light from different points in this image, I can now knowing the intensity of the light coming in and through some calibration process. So, let us say before I came to this experiment, I went through a calibration process where I put drops of a known diameter into the same light sheet and then measured the intensity of the scattered light coming towards the camera. So, from that, if I take this I proportional to d squared, I can now convert this to I being of the form k times d squared. So, k is a calibration constant that I can calculate or that I can measure from my calibration process, where I set up an experiment and have drops of a known size in the light sheet, and knowing the intensity of the light that the camera sees, I am able to measure, I am able to obtain a value of k during the calibration process, and I can use that same value of k in my real experiment, where I am dealing now with drops of unknown size, but I know the intensity. This is in some sense the basic principle by which I can add a particle sizing algorithm to a standard PIV setup, okay, where I take any one of the two images. Remember, PIV deals with pairs of images. I can take any one of the two images, get the grayscale intensity of the light that the camera sees, and knowing this calibration constant k, I am able to calculate a distribution of surface area. I do not get individual particle sizes. See, look at it this way, this green image here is a grayscale intensity, that is all what you have to deal with. This grayscale intensity at any point is proportional to the surface area, the total surface area of the drops present in there per unit volume. So, if I have monodisperse drops, then I know that I is exactly equal to k times d squared. If I have a whole distribution of drops like in a real spray, we will still say that this I is equal to k times the total surface area per unit volume. So, TSA or in some sense, instead of saying total, you might say this is the mean surface area, like an average surface area in this little green rectangle, and that surface area, liquid vapor surface area that is present in this green rectangle is responsible for the grayscale intensity, like an average grayscale intensity at that point. So, I can look at the entire image, look at where the image is bright and assume that there is a higher surface area of the drops. I could get this surface area in one of many ways. I could have a few drops that are large in surface area, locally concentrated there. I could have a large number of very small drops. So, all I know is some sense the total surface area that is available for scattering the light. So, I have now developed a methodology by which we can take the grayscale image and convert it to a surface area distribution, spatial distribution of surface area. That is essentially what you get from processing a single image. There is a problem with this approach though, and it goes back to this me-scatter pattern. Now, if I have a drop exactly at 90 degrees, this dot here indicates the sort of level of intensity I might expect that to be seen by the camera. So, if I take an image like this, like I will take this blue image, and typically, and I will draw this out separately just so we know what we are dealing with. If this is my imaging area, and if this is a camera that I have, now really speaking the camera is where your eye is. So, I am going to draw a projection of this. This is my imaging area, it is a thin light sheet, and I have lots of drops inside this light sheet. That is the whole idea. Just like these drops when projected look like this. Now, drops in one part of the drops in this edge of the image subtend a different angle. Now, mind you that we have light coming in from here, just like in the image I showed before. So, if I have light coming in from your eye towards the spray in the bottom image, the scattered light makes an angle different at different points in this spray. So, the angle made by the scattered light coming towards this camera from one of the edges of the spray is different from the angle made by the scattered light coming in from the middle of the spray. Okay, so, if my field of view is much larger than the camera aperture, which is always the case, it is very rare that you are imaging at 1:1 or less than 1:1 magnification in a typical PIV application. So, you are really looking at a fairly broad region in the spray, and so this typical angle may not be as large as the schematic indicates, but it is surely not small, it is surely not 0 degrees. If the angle is nearly 0 degrees, which is the case like in a microscope, you are essentially looking at the scatter from all the drops being very close to that 90 degrees. So, light coming in from the top and scattering light towards the observer. Whereas, if the light coming in from the top and the region of interest is much larger than the camera, then I have light being scattered towards the observer from different angles at different angles in different parts of this rectangular image. If you go back to this me-scatter pattern, the intensity of the light observed is different when observed from different angles. So, the same size drop present in different corners of this image or in the middle of the image would appear brighter or dimmer. Okay. This is a challenge because this k, the calibration constant k, now becomes a function of the scatter angle alpha. So, for different points in this image, I have to know what the angle over which light is scattered towards the camera. So, I know the angle of the incident ray in some frame of reference, and I know the angle subtended by the scattered ray towards the camera. I mean, I am using ray tracing arguments, but for now this is sufficient at least to get a qualitative picture of what is happening here. So, the angle subtended by the scattered ray coming towards the imaging frame, imaging plane, the angle between these two is essentially what we saw here as this theta. This is the scatter angle. So, if I take a an imaging frame like this, I need to know the scatter angle for all the points in this imaging plane. So, for example, if my camera is right above the imaging plane, the light scattered from the top right corner of the image versus the middle of the image versus the bottom right corner of the image would be different, and I need this k at different points in order to get a quantitative picture of the total surface area distribution. This is a challenge and can only be addressed through proper calibration. So, I populate this light sheet with drops of a given size, known size, and get the image from different, get the entire image over the frame, take the entire frame, and knowing that I am supposed to get the same grayscale intensity at all points, as though I was looking at the entire image from the same scatter angle. That is where the calibration constant k has to be derived. Now, some of it is pure geometry, where you get the scatter angle and estimate the value of k given I and d squared at that point. There are other sort of more optical effects which are aberrations that have to be accounted for when you are doing light sheet imaging like this, but we will not go into that at the moment, because we are only looking, we will only focus on sizing and velocity measurements for now. Okay, so if I was able to get a k as a function of alpha, I have a way of taking one of the frames in a PIV imaging system and get an estimate of the total surface area in different points of the image, and I will take the surface area as indicative of the size at that point. Okay. That is a possibility, that is a method by which we can get some size related information in a PIV. We will move on and talk about another instrument that is very widely used in particle sizing, called phase Doppler particle analyzer. A phase Doppler particle analyzer is an instrument that measures both size and velocity information at a single point. Okay, the basic construction is as follows. Take a light beam, a laser, you do require a laser here. For PIV, really you do not require a laser. There have been some studies where people have used reasonably high intensity LED sources to get PIV, because all I am doing is imaging. I am getting two snapshots of a moving set of particles, and I am not taking advantage of coherence in the light source to in a typical PIV system. The one big advantage that a laser has still is its intensity, because it is a collimated and coherent light source. It remains a very high source, it is a very high intensity light source, and intensity matters in a PIV because the if I go back for a moment, this I is the scattered light intensity. Really speaking, I should strictly write this as I by I naught, where I naught is the source light intensity. So, for the same I naught, if I increase I naught for the same d, I am likely to get a higher intensity of the scattered light back towards the camera, which also means that if I take a certain source, if I take a certain I naught intensity of my source light And if my camera has a threshold of detection, that is, it is unable to sense intensity levels below a certain lumens or whatever unit you are comfortable dealing with, then that intensity level determines the size of the drop I am able to detect. So, if I want to detect very small drops, I do require a high value of I naught, because I by I naught is the ratio that scales with d squared surface area. Okay, same applies to PDPA here. So, I take a laser of a certain intensity. There is a mechanism involving there is a construction involving beam splitters and mirrors inside here, which I mean it is not really important, but essentially I create two laser beams. And in one of the path in the path of one of the beams there is a phase shifter. Okay, this is often called a Bragg cell. It is a small, it is like a piece of glass if you want to imagine it in very simple terms. If I put a small piece of glass in the path of one of the two beams versus the other, I am going to shift the phase, because the optical path length is proportional to the refractive index times the physical length. If the refractive index of air is 1, the refractive index of glass is higher in relation to the 1. So, I am going to create a higher path length for this bottom beam in relation to the top beam. So, that is the simplest way to think of this. So, if I take the light here, if I plot the wave intensity or wave amplitude as a function of time, if the top beam has an intensity that looks like that, on the same plot the bottom beam may be slightly shifted in intensity, shifted in phase. So, this phase shift, you can call it a phase shift in time or a phase shift in phase angle. This phase shift is important, we will see later. So, the moment I take two light beams that are of the same wavelength and potentially even of the same intensity, we will come to that in just a moment, but one phase shifted in relation to the other, okay, you see some very interesting things. So, the next part of the construction is that there is a convex lens that you use to focus these beams down to a single point. This forms my measurement volume. So, we set a point, but it is really a measurement volume, because each beam is approximately about 1 mm in diameter, slightly less than 1 mm, typically 1 mm. Now, if I take two beams that are approximately 1 mm in diameter and form an intersection, you are essentially looking at the intersection of two cylinders that are 1 mm in diameter. So, this is your measurement volume and it is typically about 1 mm cubed. So, this is a point measurement instrument, point that averages information over this scale of length, about 1 mm. Now, this part is called the transmission optics. So, this is called